So our third plenary talk this morning is being given by Miles Padgett. Professor Padgett holds the Kelvin Chair of Natural Philosophy at the University of Glasgow in Scotland. His group has pioneered the understanding of light's momentum, including conversion of optical tweezers to optical spanners. I think it's a term that he may have invented. The opportunity for angular momentum in optical communication, and demonstrating an angular form of the quantum EPR paradox, amongst many other things. So Miles' title this morning is Light in a Twist, Optical Angular Momentum. Please join me in welcoming him to the stage.
Always a relief to see that the data projector has actually worked. I was getting a bit panicked there. Well, thank you very much, David, for that introduction, and thank you and the organising committee specifically for the opportunity for me to come and speak to you all here about an aspect of physics which has pretty much interested me for the past, it seems a long time now, 20 years, since in 1992, Les Allen and Han Verdman introduced the world to the idea that one could generate light beams in a laboratory that could carry an angular momentum additional to and independent of the photon spin. And I'm going to talk a little bit about some of the things that have happened in the past 20 years this morning. First of all, I just thought I would start off with a picture from my office window. Oh, if that were true, a nice picture of Scotland, suitably photoshopped to give it a blue sky. That's a sort of a once-in-a-decade view of a loch about 30 miles north of the laboratory. And anyway, you can see what I plan to do this morning. I'm going to start off and really just try and give a little bit of a tutorial to those that are unfamiliar into what orbital angular momentum is. I'm then going to just review some of my favourite papers, not written by me, I hasten to add, but the papers written by other people that I wish I'd written. I guess we all suffer from that. And then finally, I'll talk about some of our ongoing work in Glasgow. So let me just ask a question, and I'm sure it seems a pretty obvious question, but it's a question that I often ask our undergraduates. Of course, we know that a photon carries a spin angular momentum of h bar. How is it then that a multipole transition can conserve angular momentum? If I have a quadrupole transition, the angular momentum of the molecule or the atom changes by 2h bar, and the photon only carries h bar. So where did the extra angular momentum come from? And it's long been recognized, and I say long being recognized, it's been recognized since at least the 1930s when Charles Darwin wrote this paper, Notes on the Theory of Radiation. I should stress at this point that it's not the Charles Darwin of evolution, but interestingly, his grandson. Isn't that interesting? I thought it was interesting anyway. Okay, so Charles Darwin's grandson, also called Charles, wrote this paper, and he considered specifically the problem about where does this extra angular momentum come from or go when a quadrupole transition happens. And he said everything was fine, providing you think of the light, it looks like it came from slightly the wrong place. Imagine I've got a laser pointer here in my hand, and I fire the laser pointer. I can exert a torque with that laser pointer about my body, and the longer my arm gets, the more the torque. So the idea that linear momentum acting at a radius vector can exert a torque is, of course, not new. And so in that sense, the idea that there was more to light's angular momentum than photon spin had been recognized, I say, at least from this time maybe somebody knows of an earlier reference. Now, moving forward to the paper that I've referred to already, this paper in PhysRev A, just to show you that all good papers do not necessarily get published in Nature and Science. Other journals publish good papers too. This paper in PhysRev A, were by Les Allen, Han Verdman, and their co-workers in Leiden, introduced this idea that this extra angular momentum was not just a very rare consequence of an almost forbidden transition, but it was possible to generate laser beams within the laboratory where every single photon was in this higher angular momentum state. Now, I didn't read the paper in 92. I read it in 94 when I met Les and had dinner. And Les said to me, "Do you know, Miles, that if you shine a laser at the stem of this wine glass, you can introduce an angular momentum such that in principle you could transfer that angular momentum to a mechanical object?" And he was referring to not the birefringence in the wine glass that would change the polarization state, but he was referring to the wine glass as being an example of a cylindrical lens. And indeed, in that 1992, in the paper that just followed it, the Beiersberg and et al. One, they showed that cylindrical lenses, when inserted into a Hermite Gauss beam, would convert it into a Laguerre Gauss beam. What does that mean? Here I've got two little sketches of, so these surfaces here are the surfaces of constant phase. On the left-hand side, we have a plane wave. We have a plane wave coming towards you. We have an electric field and a transverse magnetic field. And I do E cross B, and that gives me a pointing vector absolutely parallel and collinear with the direction of propagation. And so if I shine one of these laser beams at you, it pushes you away. And we heard from one of the earlier speakers this morning about this idea of optical momentum forming the basis of optical tweezers. Now, that's not the only solution to laser modes, and indeed, another kind of solution one can get is the one that typifies the Laguerre Gaussian beams, where the wavefronts are not plane, the wavefronts form a helix. Now, one can see straight away, looking at that little diagram, that if I now think of the transverse electromagnetic fields, they are in the sort of surface of the helix, and so now, rather than being like this, with a pointing vector coming out towards you, on the one side of the beam, lean over backwards, and there's a pointing vector pointing upwards. On the other side of the beam, lean over forwards, there's a pointing vector pointing down. And so we can see that the linear momentum, so to speak, of the light has an azimuthal component, and therefore the beam on the right-hand side there carries an angular momentum in the direction of propagation, which is absolutely nothing to do with its polarization state. Nothing to do with the spin of the individual photons. Rather, it gains its property from the phase structure of the beam. Now, let's just contrast some things. Hopefully all these movies will come to life. Yes. At the top there, top right, I've just got some little animations showing the evolution of the electric field for right-handed and left-handed circularly polarized light, where we would say that the ratio of the angular momentum to the energy is h bar divided by h bar omega, or 1 over omega. And for circularly polarized light, I only have two states, right hand and left hand. Now, for the orbital angular momentum states, we've already seen the L equals 0, that's the plane wave, that carries no angular momentum. We've seen some L equals 1, but a single start helix isn't your only option. You can have a two-start helix or a triple start helix. The triple start helix is a pasta fusilli. If you look at a pasta fusilli tonight, you'll see it has three little helices intertwined with itself. And I could have -1, -2, -3. Indeed, I could have +4, +5, +6, +7. And so, whereas there are only two orthogonal states of spin angular momentum, there's an unbounded state space for the orbital angular momentum. And that immediately perhaps suggests one possible range of application areas, which I'll come back to, namely this, Bob Boyd's always fond of posing the question, how much information can a photon carry? Clearly, using the polarization, it can carry a 1 or a 0 in terms of information. If I use the orbital angular momentum, it can carry a 1, a 2, a 3, a 4, a 5, a 6, and so on and so forth. So let's just take another look at the same videos there, but I want to imagine now that one of these beams is coming towards you. What would you see? Well, if I shine a normal laser beam at you, you get something like you see on the top row. But now let's have a think about one of these helically phased beams. If I ask you, what's the time at the North Pole? You tell me, oh, not sure, because all the time zones come together. Has no time. Well, if I ask you now, what's the phase at the center of one of these light beams? You go, oh, not sure. All the phases come together. So there's a phase singularity at the center, and associated with that, the intensity always goes to 0. So one of these funny twisting beams has no intensity at the center and no angular momentum at the center. It sort of increases. The intensity in the first case increases parabolically. In the second case, it's r to the 4. The third case, it's r to the 6. Which I think actually is another way of understanding why quadrupole transitions are rare. Because the overlap integral between the atom and the middle of that beam ain't very high, because it's dark. The next to that just shows you a phase cross-section, and that's another way these things are described. The first one, as you go around the azimuth of the beam, the phase changes by 2 pi. The second one changes by 4 pi. The third one changes by 6 pi. And then also, what I've shown there is if you interfere a beam with its own mirror image, because now the phase is going opposite directions, you get constructive and destructive interference when you overlay the beams, and you get these rather attractive petal patterns. And indeed, one might use those petal patterns in order to quantify the L, or the angular momentum, that you have going. Now, I'll just say something else which is a little bit surprising. Hopefully, I sort of persuaded you that this helically phased light beams, they do carry a real angular momentum. I'll show you some videos in a moment. The thing that's perhaps a little bit more surprising is, why should it be quantized in units of h-bar? The right-hand circularly polarized light carries h-bar of spin angular momentum. The L equals 1 also carries angular momentum. Turns out it's also h-bar. So what do the two things share in common? And of course, what they share in common is the rotational symmetry. And that's why the quantization arises. And so another useful picture to have of one of these light beams is that we've got this ring of light coming towards you, but the pointing vector and the momentum flow is not in the z direction, it's skewed. And so if you were a ray tracer in terms of Zmax or whatever, plotting out one of these optical systems, these orbital angular momentum beams are really skew rays. So it's the skew rays in your optical system which are carrying the orbital angular momentum. Now, having spoken about these beams, I've alluded to how one might make them with cylindrical lenses. That turns out to be quite hard. It actually transpires at the same time as Les and Han were working on their beams that carried orbital angular momentum. Marat Soshkin and co-workers in the Ukraine were also making helically phased beams. Apart from they didn't use lenses, they used forked diffraction gratings. And so we have purple at the bottom there a plane wave beam hitting a diffraction grating, but it's a diffraction grating which has more lines at the top than it does at the bottom, and therefore one can imagine that the diffraction angle at the top and bottom are not the same, and so that's going to set up a skew ray within the optical beam. You can change from L equals 1 to L equals 2 to L equals 3 simply by changing the number of prongs in your fork. And so the first order diffracted beam in that case is L equals 3. The minus first order is L equals minus 3. And of course, those of you that play with diffractive optics will know that it's possible to blaze the grating, so one can accentuate one order with respect to the other, which is why I've shown one brighter than the other. Now, that kind of approach relied upon being able to make, we'll call them computer-generated holograms or diffractive optical elements. But essentially, for about the last 10 years or so, that's been pretty much unnecessary. Why is that? Well, the likes of Hamamatsu or HoloEye or Boulder Nonlinear Systems will sell you these liquid crystal spatial light modulators, which you connect to the video output of your computer, and whatever pattern you can generate on your computer screen, you can then relay to this liquid crystal device and turn it into a programmable phase optic. And so I've just shown a little picture of one there. And so one can imagine now from a generation point of view that one can start off with a light source, pass it into single mode fiber, collimate the beam to give you a plane wave, let it diffract into the first order and generate, in this case, an L equals 3 beam. But optics works backwards as well as forwards, and therefore it's also possible for me to replace this light source with a detector. When the detector detects light, you know that here there was a plane wave, and therefore here there was an L equals 3 beam. So you can run the whole thing backwards, replace your laser with the detector, and now one can measure the orbital angular momentum of the light instead of generating it. And if I want to change the state, I merely reprogram the thing, the device, and just in case you want to play with these patterns, Richard Bowman, one of the guys in my group, wrote this lovely little app for the iPad where you can generate, twist it. Okay, one can generate nice little holographic patterns. Indeed, you could plug that into your little SLM device and actually have a real-time control of your diffracted beam. So you can download that from the iStore for your phone or iPad, and it's free. Honest, there'll be no profit made there. I mentioned already that this was a real angular momentum, so I'm just going to show you a few little videos now, looking down a microscope at micron-sized particles when you illuminate them with light beams that carry angular momentum. You'll be glad to see that the particles spin and rotate. Double helices. Obviously, we have DNA, so we like double helices. I was just speaking in France last week. There's a very nice chateau in the Loire, I think, which has a double intertwined spiral staircase. It is said that it was built this way, so when the wife came home, the mistress could go down the other steps. Now, the other picture I show, incidentally, is from the Vatican. Clearly, that was built for a completely different reason. I don't know what it was. Now, let's just have a review of some of the things that other people have done with orbital angular momentum. So I said already that Les and Han wrote their paper in 1992. People thought it was a good paper. They saw it. But people really began to take notice when it was shown that you could make little particles spin round and round using these light beams. And that was work by Helena Rubinstein Dunlop and her colleagues in Queensland. So that's the first paper I wish I'd written, but didn't. And she was the first person to show that. And at that point, I think that's really when you can see the sort of interest in orbital angular momentum increased. I also mentioned that this use of spatial light modulators made the whole thing much easier, these liquid crystal devices. And that was a paper in 2002 from Jennifer Curtis and David Greer. Now, having spoken about these sort of macroscopic manifestations, if you remember, we started off this whole presentation with me talking about what makes a quadrupole transition possible. Therefore, clearly, this property of orbital angular momentum isn't just a macroscopic property. It must apply to single photons too. And that really was most eloquently shown by Anton Zeilinger and co-workers in 2001, I think, with their publication, Entanglement of Orbital Angular Momentum States. I might come back and talk about this later. But for now, I'll just carry on going. OAM in imaging, I've just put down two more papers here. The top one is from Monika Riechmarter's group in Innsbruck. We're all familiar with the idea of doing interferometry. And when you do interferometry of a surface, you get all these ring patterns and things, contours of equal height. And it can be a little bit, in principle, difficult to distinguish a hill from a valley, because you just don't know whether it's pointing up or down. Monika showed that by using a reference beam that wasn't a plane wave, but with a helical phase, then rather than getting concentric rings, you got a spiral fringe pattern. If the spiral went clockwise, it was a mountain. If the spiral went anti-clockwise, it was a valley. So she was able to break the up-down ambiguity in the interferogram. Grover Schwarzlander and his group have been using vortex phase masks within telescopes, the idea there being, of course, when I put a Fort grating in, or the equivalent phase mask, it takes a normal laser beam and turns it into a ring with a dark hole in the middle. How about I point it at a star? When I look at a star now, rather than being a bright spot, it becomes a bright ring with a dark center. Maybe that makes it easier to spot a neighboring planet. So, a form of phase masks. Communication. I just picked out two papers here. First of all, there was a demonstration a couple of years ago now of radio waves, not optical waves, a radio wave communication link. And you can see that the antenna disk, rather than being a smooth bowl, has a stepped phase discontinuity in. So it emits radio waves with an L equals 1, which are completely orthogonal and distinguishable from the radio waves with L equals 0, and therefore you see some kind of multiplexing opportunity. Most recently, Alan Wilner's group, University of Southern California, has published some truly phenomenal data rates using OAM as a multiplexing thing. So this isn't instead of wavelength multiplexing, it's in addition to wavelength multiplexing. It's in addition to polarization multiplexing. It's just how many channels can I get on my optical beam. We're familiar that light is a transverse wave and therefore can have a polarization, linear, circular. But what about longitudinal waves or other kinds of waves? Where the polarization, in the case of sound waves, you don't get circularly polarized sound waves, at least not in air. But on the other hand, I can control the phase. And so there's some nice work here from Karen Volko-Saduva, who showed that she could, by having an array of loudspeakers and driving them out of phase with respect to each other, create a helical sound beam. And that sound beam can set things into rotation. And just as a little aside here, the force exerted by a laser beam, as I'm sure you're aware, is the power in the laser beam divided by the speed of light. That's why you need that's why you can't move very heavy things with optical beams, because the speed of light's so high. But that relationship isn't just true for light, it's true for waves in general. The force exerted by a wave is the power in the beam divided by the phase velocity. Now, sound's a lot slower than light, so watt for watt, it exerts a lot more force. So you can actually rotate big things with sound beams. And here, some beautiful work from a number of different groups. I've just picked one because I like the picture. This is using a fork diffraction grating, fibbed and stuck in an electron microscope to make vortex rings in microscopy. I think partly with a view of doing some of the kind of optical techniques that Monica's done in the optics, but with electron microscopy for edge enhancement. Now, a bit lowbrow now. In 2004, Graham Gibson in my group published a nice paper with me, at least I think it's quite a nice paper, on using these communication states, and it was picked up by a European magazine called New Scientist that you may not be familiar with here, but the cover is one of those things that you live to die for. Twisted light, it's fast, it's furious, and perfect for talking to aliens. Not quite sure. I know what they were getting at. I can explain it later. And then, because I'm such a sucker for publicity, this is a picture. I often show this one, but I never show the next picture from the article. Oh, dear. Mike, one of my research students over there, just said, but Miles, where were your laser safety specs? I assured him it was a very low power beam, and therefore no danger at all. Now, I'm going to just talk a little bit about some of our own work, but in doing so, I just want to highlight some other key papers from the past. These ideas of phase singularities within fields became popular in sort of the modern era thanks to work by Michael Berry and John Nye. Interestingly, initially in the ultrasonic regime, they were wondering why it was when they were looking at radar echoes off the Greenland ice sheet. So send a radio wave down, and you're trying to work out how thick the ice sheet is. You'd move around with your detector, and you'd find bits where there was nothing coming back. So you send all this radar energy down, there's nothing coming back. Where did it go? Now, that seems quite a strange concept, maybe, but actually it's a concept that you as opticians, so to speak, are completely familiar with. It's called optical speckle. If you shine a laser beam at a rough surface and then look at that surface, there's positions where there's complete darkness, the black specks. So, shouldn't be surprised. And this is something we looked at specifically with Mark Dennis at Bristol, and also some people in my group at the time, Kevin and Florian. And if I just now look at a speckle pattern, that might be the intensity that I expect to see if I was to blow a bit of it up. Now, our eyes can't see phase, but on the other hand, I can do interferometry. And if I did interferometry on that speckle pattern, I would find that there are positions, which I'm marking there, which are phase singularities. All phases meet, either clockwise or anti-clockwise. Now, interestingly, for reasons I won't explain, they're all 2 pi. They're all L equals 1. They're not L equals 2. They're not L equals 3. And actually, if you look up into the night sky with a telescope and see an L equals 3 beam, then that is a sign of intelligent life, obviously because they're interested in orbital angular momentum, but because high-order vortices are not stable to perturbation. And so the perfect for talking to aliens actually was a reference to that observation, not made by me, I hasten to add. Now, this idea, so this thing that you thought was an esoteric property of funny light beams generated by forked diffraction gratings, is actually present within all optical fields. Whenever you have 3 or more plane waves interfering, you will form a network of these phase singularities. When you have 5, 6, 7, 8, the network becomes very complicated, as shown here. Now, if you think about the speckle in some plane, let's not talk about which plane, that's clearly not quite the right thing to do, because the optical energy doesn't just exist on the screen, it exists at every plane position between you and the screen. So it's a volumetric effect. If I could sort of move around with a fishing rod and measure the optical field in different places, I would measure a volume, not just a cross-section. And so that was something we set out to do. And what does that volume look like? So this now is a volumetric rendition of the lines of 0 within optical speckle. So this is just a normal optical speckle pattern created with a ground glass screen. You've then got some camera on a translation stage in front of it, and you're interfering it with a plane wave and doing optical interferometry. And the curious thing, at least curious to me, is you can see some of the lines are unbounded. They basically start somewhere at the edge of the camera field of view and percolate the entire volume out the other side. But some of the lines actually form closed loops. And this is a completely natural state, in this case, of monochromatic light. So every single frequency component of a light field in this room from that wall is riddled fundamentally with these lines of complete darkness around which the optical energy is circulating like the coil of a spring. You can imagine going round like that. I said I was going to come back to Anton's paper and talk about some quantum entanglement effects. I'm not going to say very much, but this, to say, is work that we did in Glasgow, and I must acknowledge Jonathan Leach for this, but also in collaboration with Bob Boyd's group in then Rochester, now sort of some kind of superposition of Rochester and Ottawa. And Bob said to me at a SPE conference, give a plug for SPE actually, Miles, if your group shows us how to use spatial light modulators, we'll show you how to do quantum optics experiments. And we've done quite a few together, and I thank Bob very much for that. So what's the basis on which these experiments work? Well, back in the 1990s, we'd written a paper showing that when I did frequency doubling with an L=1 beam, not only did the frequency double to go from infrared to green, but the orbital angular momentum doubled from 1 to 2, or from 2 to 4. So the orbital angular momentum was conserved in the process. Somehow the 2 infrared photons came in, 1 green photon came out, and the green photon that came out had the sum of the angular momentum. Now, if you do that whole thing backwards, that says that 1 green photon comes in and 2 infrared photons come out. The angular momentum's conserved. If I came in with 2, you might think it goes 1, 1. Maybe you'd think that. How about if I come in with 1? Does it go? We can't go half. So 1, 0, 0, 1. We see now we've created some kind of superposition of states, and that lies at the basis of quantum entanglements. And so essentially here, just got 2 slides that show 2 things that are true. If I come in with L=0 and measure this one to be L=4, I know that this one's -4. If I measure this one at -2, this one must be +2. The angular momentum must be conserved. So that's correlation. How about the complementary basis? If I want to do experiments in quantum mechanics in the linear basis, I would choose to measure position or momentum. What about orbital angular momentum? Well, what I do now is I choose to measure the orbital angular momentum or the angular position. And measuring the angular position is easy. Even Quentin Tarantino can measure angular position. Think of that bit from that with the little things. You just have your little triangular masks and you move them in front of the detector and see what the correlation is between the angular states. And when you do that, you find you can see correlations in either basis, and hey presto, that's a manifestation of the Einstein-Podolsky-Rosen paradox, not for momentum and position, but for angular momentum and angular position. Now, I'm just going to skip on from this one to say 2 other things. So this is work, Martin Laver is here, and he's talking about it later in the week. It's also done with Johannes and Joris from the Leiden group. And the problem basically is this. With spin angular momentum, there's 2 states. I would like to be able to measure them. No problem, I use a polarizing beam splitter. How about the orbital angular momentum? I need to replace the polarizing beam splitter with some kind of fan-out optic, which can map the states into linear position. And to cut a long story short, this we basically did, thanks to Gordon Love and his colleagues in Durham, making us some very strange lenses, where the incoming beam, which is a bagel in Bob Boyd's language, comes through and becomes a hot dog. Okay? The azimuthal phase change around the bagel becomes a linear phase change on the hot dog, and so that's a tilted wavefront, which means a lens focuses it to a different position. And here we see the output plane at the camera of the energy as I change the input orbital angular momentum state. So all the energy is moving from bin to bin as we move across. Now, let's just look at these two videos again. This is my last item. We have the beam with no angular momentum, and we see that an evolution in time is like a movement in Z. Z and time are indistinguishable from each other. How about one of these helically phased beams? Well, not only now do I have Z, but I have theta, and I see that theta and time are indistinguishable. A time-evolving wave looks like a rotating wave. Now, drawing analogy to the Doppler shift, if I run towards a light source, I see it blue shifted. But with one of these rotating beams, I don't need to run towards the light source. I just need to somehow attach myself to the wheel of death and spin it round and round, and I should see a frequency shift. Now let's just think about what I'm talking about here. There's a form of monitoring which we might call speckle velocimetry, whereby I shine light down on a rough surface like this table, drag the table towards me, oops, nearly broke it, that would have been a good end, drag the table towards me, and the light that's scattered to my eye is Doppler shifted. And it's Doppler shifted V over C, but also with this extra angle cos theta, the angle at which I'm looking at it. I see the biggest Doppler shift down here, and then smaller Doppler shift up there. And I can do that not for the linear case now, but for the rotational case. So I want to look down on a spinning disk, so I'm not moving towards it or away from it. I'm just watching it come, and I'm going to not look at the linear momentum state, I'm going to look at the angular momentum state. And remember, the angular momentum state is these skew rays. So they're all coming in at an angle. Go through the maths of that, and you expect to see a frequency shift between the positive and negative angular momentum states, which is equal to the rotation of the disk multiplied by the L number. And that is something that Martin has just been working since Christmas. Well, actually since before Christmas. It's taken us a while. So we're illuminating a spinning disk with light. We are collecting the scattered light, but only collecting, in this case, the plus L18 and the minus L18. We're selecting those with our hologram and taking the light, both of those, into the single mode fiber and onto our detector, and hoping to see what we see there, a beat note. So this is something going round and round, not changing the distance between source and observer. I'm just rotating the frame between source and observer and seeing an angular Doppler shift in the scattered light. So I just wanted to finish at that. Just running out of time. So I'd like to thank you for all coming this morning. I'd like to thank my group, both past and present, for making the last 20 years of my professional life such fun. If this is a field that's interesting to you, then David has organised a number of sessions which I think take place in 238, we decided, later on today. If you would like to read more about it, there's a few review articles, including a SPE newsroom video, which I made last year, but also, and perhaps most relevantly, I've burnt a few copies of my talk to Glasgow University memory sticks, which I will happily give away to anyone who wants them. The good news is you can delete the talk and just use it as a memory stick. So, thank you all very much, and thank you again, David.
Thank you very much. We might have time just for one or two questions. I think there's one there.
So do you think there is any chance to do this angular momentum in a guided wave configuration? Or there is any work with waveguides where you can have some...
Is there any chance of doing angular momentum in waveguides? That's a very good question indeed. And indeed, a number of people are looking at doing exactly that in fiber. The problem is with these angular momentum states is that they're different modes. And so if there is a mechanism which couples energy from one mode to another, you're in trouble. So even when you shine these modes through atmosphere, the effect of atmospheric turbulence to some extent is to create mode coupling. If you put them into waveguides, and then the waveguide goes around the corner, then you're going to have mode coupling. Now, having said that, you can then start thinking about ways in which you can make the modes non-degenerate, so they won't couple energy into each other. You can think about some other form of guiding in the form of photonic crystal fiber. Philip Russell and the Leiden group have been looking at that. But waveguides create a problem. And now, I just want to say something else. There was some, particularly in the BBC, ran a story on doubts over twisted light, partly due to this communication thing. At the end of the day, it's just another mode. And so if you actually think about the link I have in a communication system between me and you, in terms of the number of low-loss modes that I can send, that depends on the Fresnel number of the link. Whether I choose to encode it into orbital angular momentum modes or Hermite-Gauss modes or Bessel modes or whatever else, to a first approximation doesn't matter. So although the orbital angular momentum is different from the wavelength and different from the polarization, it's not different from spatial modes. It's a spatial mode in my view. Some people might disagree, but so it's not magic, sadly.
Thank you. There's a question here.
Just a quick question. I saw a black dot at the center of the beam. How could you control the size of the blackboard, make it larger or smaller?
How big is the black hole in the middle of the beam?
Yeah, there's a black hole inside.
So the black hole in the... Okay, so if you take one of the single ringed beams, how big is the single ringed beam compared to the Gaussian mode that you might have used instead? The radius of the ring is root L divided by 2 times the beam waist of what would have been the Gaussian. And so if you go to larger and larger L, the beam gets bigger and bigger. And essentially, if you're going to try and measure it with a telescope over there, you're going to need a very big aperture. Now, when it comes to the center of the beam, the intensity is 0 exactly at the center and grows polynomially coming out, and that grows with 2L r to the 2 mod L. So for the L equals 1, it's a parabolic growth. There was a fascinating paper at Snowbird this year about somebody using I didn't really understand it, a metamaterial lens to change so that the radial component of the K vector was not quite what you'd expect it to be, and they were using that to generate a beam with a very small black hole in the middle. So you're able to concentrate the energy closer to the beam axis. And so there's maybe ways in which you can, even with high L, get the energy sort of close to the axis. It's a very interesting idea. But in free space, what I said was true.
Okay, time's moving on. We probably should draw to a close. And I think the audience will all agree with me. We've had a fantastic, very exciting program this morning. So let's take the opportunity one last time to thank Professor Padgett and all the speakers. Thank you.